Data science. What, why, how? These are usually the questions. So by the end of the workshop today, you have some sort of understanding of the fundamental concepts in the world of data science, have some idea of assessment of like what are the real world applications of the field, including careers, and then use the Kaggle platform. We will show you a little tutorial about Kaggle. And of course, if you want to enter the data challenge, you can feel free to do so. So it's really from theory to application is what's important. And we will share those resources for you for those of you who probably joined late and probably didn't get to access them. So as I said before, I will always start off with data science has its origins in math, statistics, and computer science, which have been around for a number of years. And what's really nice about it is that now we're not working in isolation in these three domains. We actually come together quite nicely to be able to harness the tools and the power of all these fields. So I'll always really tell people, if you want to know what data science really is, goes back to math and statistics foundations, and of course, computer science. And now it's grown quite tremendously. You're hearing things about machine learning, you're hearing about artificial intelligence, Internet of Things. And what's nice about it is that we can use the data we have to turn it into meaningful insights and actions, really, which is really what we want to do. So that includes things like data mining. We have other things like cleaning the data, analysis, visualization, and of course, we want the insights to be able to tell us how we could help change the world. So this is really one of the, I would say, quotes about what it involves on a much larger scale. And I think people sometimes just think about it in an isolated sense, like it's just statistics and math and these things coming together. But just remember, we have data in so many different fields. So you have to think about the subject matter that you're in, the domain that you're in, if you're in business, if you're in education, if you're in medicine, and how you could use that data to actually be able to build something meaningful. Why does data science matter? So it's really because we have a few different things that we have to think about. Converting valuable information. Data is meaningless unless we convert it. We have large amounts of data. We have big data that is sometimes organized, but in a lot of times it's very unstructured. So we need to discover the patterns. It also has a wide range of applications in our daily activities. I think we are all data scientists in real life, to be fair. And as I mentioned, it's really an interdisciplinary field where it's not only just the math, statistics, and computer. I'm thinking business and healthcare and climate change and all of these fields, things that matter to us, are an integral part now of the data science realm. So this, I know it's a loaded slide, but it's actually just giving you some of the applications in real life. Of course, in this challenge, and in the data we will talk about today is really to analyze patient data and identify patterns to make predictions. So in healthcare, we could see where it comes in. We could also see in climate change with respect to predictions in terms of natural disasters. And of course, transport, optimize traffic flow, reduce congestion, finance, predicting in terms of the market trends, detecting fraud. Then we have things like e-commerce, personalization of recommendations, and improving the customer experience. Even when you're on Netflix, Amazon, all of these places, and they tend to give you, the customer segmentation with the items that you like, the movies that you like, it uses data to do that. And then of course, things like image recognition, right? To be able to classify and recognize images as well. So that's just a few of the examples, but the possibilities are really endless. And this was a really interesting example that we came across, which really deals with the healthcare field in terms of Google AI, which developed deep learning, and how you can use that image classification in terms of, in particular, looking at lymph nodes and, of course, breast cancer tumors. So you could see on the left, the dark zone, and how you would have seen it before in terms of the processing quality, and it was poor. And look on the right side now, they developed a tool where you could identify the tumor in terms of the region and then classify the surrounding areas. So we are, it's really getting so advanced, all of these applications. And then of course we could turn these images into data, tangible insights and data that we could use to make some predictions about this. So just to quickly talk about the data science life cycle. Well, let's look at the basic components. if you're someone who has a statistics background, or if you have done statistics in any form, even in terms of business, you would really think about, you would have to identify some sort of problem. And of course, you'd have questions. And that's the requirements of whatever project you have or whatever problem it is that's in the real world. Then you would have to go about collecting data from relevant sources in different forms. And we'll talk about structured and unstructured very quickly. We'll have to process that data because, you know, you have to fine tune it. And that's really critical for the steps that we have to take in the analysis. And what you would recognize is that when we speak about the analysis, we would realize that a lot of the time we would spend in the data processing and then what we call like the data cleaning, etc. Because that is key in any field, regardless if it's data science, even if it's statistics, if it's just a simple problem that you're doing with a small data set with a survey, you have to look at the data, see if there's a lot of missing values in these things to determine how well the data, how robust the data is for what you want to actually predict. If there's a lot of missing values, you might tend to think maybe this is not the best data set for making a prediction or building a model or giving some sort of insight to someone about whatever the problem is in that sense. In the data science realm and in the data analysis realm, you're going to notice that we will use some more technical models that are going to sound really strange, but they all based on, if any of you all have heard of regression, majority of these models have a regression background in terms of prediction aspects. And we also look at classification type models, which is something we will talk about a little bit more in terms of the data challenge and how we can use these two types of predictions for the specific data that we have. The data modeling in itself now, when we prepare that model with different metrics, we can see now in terms of as we will talk about testing and training sets and validation, how that helps us to view the data in a sense of, is this data doing what it's supposed to? Is it predicting it well? And then we could form a model and deploy that model. And then there you go. You'll be able to have a desired model to say, well, I can use this now to make further predictions. So that's what it is in a nutshell. And that's how we will show you the full data set today in terms of the actual data analysis from beginning to end. But in the coming weeks, what we're going to do is we're going to break down specific parts. So if you're feeling like it's a lot when you see the notebook, don't be alarmed. It's really to kind of reverse engineer. You're going to start from the end and see how it looks to a data scientist, look at the different parts, and then each week we will go into separate parts of it. So next week, we'll have one of our mentors, Miss Malini Ramaran. I don't know if she's in the chat. And she will actually talk to you all about data science tools, even for persons who are not usually in data science, like, for instance, people who use social sciences packages like SPSS, even persons who use MATLAB, which is also a great tool for data science as well. And of course, some of the main ones that you might be hearing now, which we'll talk about today, would be using programming languages, including Python, as you see on the screen. Also R for people who have that statistics background. I'm very R is like one of my favorite tools. But I would also say I'm also a very big fan of Microsoft Excel or Google Sheets, those spreadsheet type programs that are point and click that you could get quick insights from. So you have a number of things, and then you have more advanced things like TensorFlow, etc. But all of these things are to tell you that there are different tools that you can use when you're exploring your data and want to build a model, but there will be ones that may be better than others in terms of the performance and the size of the data set, etc. Now, it brings us to machine learning, and that's something that you have been hearing a lot about, and you're probably thinking, well, how does that fit into data science itself? Let's have a look at that quickly. So machine learning is really a computer's ability to learn without being programmed explicitly. So it really, you'll be able to make predictions now. You see it's in the realm, it's like you have artificial intelligence, where you have machines to think without human intervention. And then within that sphere, you have what we call machine learning, which uses these statistical learning algorithms to predict patterns over time. And then within that, you have deep learning. So there are different layers. And the machine learning aspect, you'll see that comes in a lot in our data analysis portion with respect to data science, because we want to make these predictions and we want it to predict as well as they can. So I'm just going to touch on this very lightly. For those of you who want to know more about these specific aspects, we will go more into the actual theoretical and then more interactive aspects in workshop 4 on these models themselves. But we will touch on them today in terms of what they look like. So supervised learning is what we would usually be doing, where we would have something based on looking at the specific data that we have, predicting tasks for predicting labels to get new labels for the data. So we could actually have that learning problem. It's learning from the data in a supervised way. And you could actually classify it. You could actually have it as a category, or you could have it as a regression problem. So there are different ways that you can look at the features in the data, and that will tell you how you will predict, what kind of prediction that you would want to use. Do you want to label it as a yes and no problem? Like when I do student retention, it's either they dropped out or they stay in the system. Or do you want it to be a regression problem where you're looking at it in a numerical sense, maybe over some specific time, etc. Unsupervised learning is really unlabeled data, which finds groupings and structures in the data. Now, we wouldn't specifically do that right now in this portion of what we're doing for the datathon, but it's something that you can go further into if you would like to. And here's just a fun diagram to tell you that cycle for machine learning in itself and how that looks and how it falls into the whole scope of everything. Collecting the data, defining the objectives, and which is really part of what we were speaking about with respect to the data science life cycle. But you would see now we went a little bit more in depth in terms of things like cleaning the data, looking at the variables themselves, seeing if we need to look at creating new features, if there's too much missing data, how does that impact the model? Is there any bias involved in when we look at it? So I'm asking you all these questions now so that when we go through the interactive portion and we see some graphs, and we actually clean the data, and then you see graphs, and we change some part of it, you see another graph, you'll actually see how it changed in terms of we took out something from the data and we looked at it in a different way. And the exploratory data analysis is very, very important. So they call that EDA for short. And then that funnels into the data processing aspects, and then what we call the training and evaluation and deployment, etc. So I'm not going to go through this in detail right now. As I said, these are the steps that we will go through in the file, but just to let you know, this is how the exploratory analysis would look, where we look at the attributes and different univariate for one variable or bivariate for more than one variable, two variables, etc., multivariate, multiple variables, looking at relationships, correlations, types, interactions. And we look at these things first because we want to see if there's some relationship before we jump into the modeling aspect. So that's key. And then we also want to think about even identifying outliers. Besides the missing values, is there something that's making the data very biased? Is there something we could take out of the data? And that leads to what we call feature engineering, another big term, but it's really just looking at variables or features and then determining what we want to do with them to collect more insights for further data analysis. And this is the key part. So when we actually do our analysis, we'll be looking at training and testing and then evaluating these machine learning models. So just on a high level now, you could see the way it looks is that we look at building our machine learning model on the training set. And the training set in itself provides the outcome, or sometimes you would call that the ground truth. And this is used to create new features. And then we'll have a test set. So you will see these terms on Kaggle when you actually go to download the data. So it's important that you understand what they mean because you'll have these different files to work with. And you would see how well your model performs on the test set based in terms of the unseen data. Because remember, we want to actually make a prediction of data that we could probably get in the future based on this particular model. So you have to use the test set, use the model you trained for the prediction. And then, of course, you could validate those results in the end. This may look a little complicated to some, but this is just like a high-level view of preparing the data, building and training the models and what that entails, and then deploying and predicting. I know it's some very big words in terms of hyperparameter tuning and all these things, but when you see it in steps, and it's actually all involved in when we talk about the actual data life cycle, you would see how each part works with each other to make a robust model. So what you will be doing in the challenge is that once you reach the prediction stage or you build a model, you would eventually want to consistently see if there were any aspects of the model that you can improve. And that's what happens in real life with these models. They are consistently being trained to ensure that they are really the most accurate model for the problem. These slides I'm going to just breeze through very quickly, and I can also post the slides in the link for you all so you can always go through it on your own time. But these are more just kind of a stepwise look at all of these steps and giving you snapshots to people who probably have different backgrounds. Like here you would see data collection could involve for persons who in computer science, web scraping. I know people who in social sciences will do more things with surveys. You would have people who are looking at APIs, data acquisition, etc., data mining. All of these things are part of what we call the data collection process, and you could have a combination of them. Then the data cleaning that's the aspect where we say that's really one of the most important parts. And this would really help you to figure out if you need to fill in gaps in the data set in terms of the missing values, which we call impute the missing values. If we want to look at identifying anomalies in the data in terms of the outliers, if we want to convert different types of data, because remember we could have numerical data, we could have data that are more in terms of categories. So if you want to encode them as categorical, you could actually change your features and that sort of thing, and then scale them. So I always tell people, and this is even just from statistics, the variables that you have and the way the variables look are really important to tell you how you deal with it. Is it a numerical variable or is it a category? And then you could have variables that you could actually change them into different formats. For instance, you could have like, say, body mass index, which could be a number that's recorded by a doctor. And then someone else might say, well, I really prefer to look at this in a category of maybe small, low BMI, medium, high, whatever the categories are. So you can actually change your features to suit depending on the problem. Most of us should be familiar with some of these types of graphs. So I'm just mentioning some of them, and they go with the different types of data. So you'll see that in our breakdown as well. Just to remind people, as I said, for beginners, what we will be looking at first is really visualizing the data. That's the first thing you should do with any data set, because you really want to see how it looks before we just jump into trying to figure out how to model the data. And it really goes with different types of visuals, which we'll talk about further in our next workshop 3. We will talk about the data visualization. And then, of course, the machine learning aspects, as I mentioned before. There are other aspects like reinforcement learning and deep learning, as I said, we wouldn't go into right now. But the supervised learning is really important for us to train the model with labeled data to make those predictions. And I just put in this for anybody who's more advanced in here, if you're into natural neural processing and that sort of thing, text classification, sentiment analysis based on sentiments expressed in text. And then, of course, topic analysis, speech recognition, all of these things are important. So we also have all of these things you could see as part of the applications. And as I mentioned before, we had specific applications I spoke of initially with data science, and machine learning, of course, will involve some more detailed versions of these applications in terms of even self-driving cars, the traffic prediction, product recommendations, as we said. So it's really a vast area. And because of the applications, there are a lot of different career options. So people would think it's just a traditional data scientist, but I would say a statistician also acts as a data scientist as well, because as I always would say, data science really has a lot of the origins in statistics. And of course, a data analyst would do similar things. But of course, computer science is really plays a key role now because of all the software we have, because we have moved from just paper-based into the more virtual realm. And then you have like data architect, you have technology officers, you have a lot of different people, market research analysts, data application architects, etc. These are just a few of them, but it's really vast. And of course, I think you all know there are a lot of courses online that support the field as well.